One of the most practical ways to study resistor circuits is to build circuits with light bulbs. It's a very common activity. It's included in lots of elementary science curriculum, having students build circuits with light bulbs and comparing the brightnesses of the bulbs. Well, one of the first things that's usually done is you give the students a dry cell, a flashlight bulb, and 1 or 2 wires, and you ask them to make the bulb light using only 1 wire. There are actually 4 ways that you can do this. And so if you were meeting and you were doing this, you might be able to figure it out in just a few minutes, or it might take you considerable time. Most students start out by putting the wire on the bulb and then connecting the wire to the dry cell. So making the wire go from the bulb to the dry cell. But you see that that doesn't work. They might try the other end, put it on the negative side. Still doesn't work. And so it could be frustrating, but students can eventually figure it out, and many do. I will go ahead and show you how it's done with 1 wire, but I won't demonstrate how to do it with 2. So if I take my wire and I connect it to the negative of my dry cell, I can take my bulb and set the bulb on the positive, where the button of the bulb is touching the positive of the dry cell. Then my wire has to touch the side of the bulb, the metal, not the globe, not the glass part, but the metal, so that we're connecting wire to the side of the bulb, and the bulb is connected to the button. The button of the bulb is connected to the dry cell. A second way to do this is to put the bulb on its side so that the positive end touches the side of the bulb, and the negative, the wire going to the negative end, will touch the button of the bulb. If I can get it just right, there it's glowing. There we go. The other 2 ways to do it are to do the same thing, but on the other end of your dry cell. So like LEDs, it mattered which was connected to the positive and which to the negative. These bulbs, it doesn't matter. So I've got a wire going from the positive of the dry cell to the side of my bulb, and the bulb button is touching the negative. Then I could make the side of the bulb touch the negative, and my wire connect to the positive, or to the button of the bulb. So the way to do this with 2 wires is you still make a wire go, and you still have to touch the side, and you have to touch the button of your bulb. But instead of putting the bulb directly connected to the dry cell, we just put a wire in between the negative of the cell to the button. And then we could turn it on its side and connect the wire to the button, and then run a wire from the negative of the cell to the side of the bulb. And then we could do the same 2 things on the other end. So it's a lot of fun, and it's quite puzzling to a lot of people to figure that out. But the reason you have to do it that way is that the filament in the bulb has to be connected, one end and one end to the positive and the negative, just like this. But instead of both wires coming out the bottom of the bulb, like they do with the Christmas tree bulb, 1 wire goes to the side and 1 wire goes to the bottom. So that complete loop, we could say that current might go up through the button, through the filament, and then out the side, or it could come in from the side, go up through the filament, and out the bottom. So you can take a large regular light bulb and cut off the bottom of it, and you can see the 2 wires, the one that comes straight out and the one that goes to the side. That's why the threads on light bulbs are always metal. They have to conduct electricity. So after doing that, we can start building light bulb circuits and looking at the brightness of the bulb and how it changes when in different circuit arrangements and with different power supplies. The science supply catalogs will sell these light bulb holders and light bulbs, and you can buy these and connect your wires to these to make circuits. But to buy this, it costs about $3, and you get one bulb and one holder, and you're going to pay about $3 for it. The most economical way to study light bulb circuits is to use Christmas tree bulbs. After Christmas, you can buy a strand of these bulbs for $1 or $2, and you end up paying 1 or 2 cents per bulb. And not only do you get a lot of bulbs for only a penny or 2 apiece, but you get a lot of wire left over that you can use in other activities. There is some assembly required, so a wire stripper, you can cut wire with scissors, but the wire stripper makes it nice and easy to take the plastic insulation off of your wires. So once you assemble that, you have a lot of bulbs that you can use in lab activities, and you don't really worry if these get burned out because they are very, very inexpensive. So the first thing we want to look at is, how does the power supply arrangement affect the brightness of the bulbs? So I'm going to take a single light bulb and connect alligator clip wire to one side, and I'll go to a single dry cell. I'll connect alligator clip to the other side of the bulb and go to that one dry cell. And you may be able to tell that the bulb is lit, but it's not very bright. If I go to 2 cells in series, bulb got brighter. And now I go to 3 and 4 and 5 and 6. So it's pretty obvious, as more and more cells were connected in series containing a single light bulb, the brightness of the bulb increased. So why did it get brighter? Well, there are 2 ways to look at this. We know that when we put our cells in series, that gives us more voltage. 1.5, 3, 4.5, 6, 7.5, 9. So the voltage goes up. So this bulb gets all 9 volts. But also, when the voltage goes up and this resistance doesn't change, we get more current. Current is voltage divided by resistance. I is V over R. So we could say that adding cells in series increases the voltage, which puts more voltage on the bulb to make it brighter, or getting more voltage gives us more current that makes the bulb brighter. Brightness is related to power. Power is V times I. Potential difference times current. So if we want the power to go up to make our bulb brighter, we can either make V go up, or I go up, or both. And in this case, we did both. We get 6 times as much voltage and 6 times as much current. This bulb, powered by 6 cells, has 36 times the power of when it's powered by a single cell. So what if we put our cells in parallel? So we're going to take our single cell, and I'll connect another one in parallel. What happened to the voltage? Let's put another one. Doesn't appear to be changing. We'll go with another, and another, and another. So as more and more cells are connected in parallel, the voltage or the brightness of the bulb stays constant. It doesn't change. Well, why not? Well, think about it. What happens to our overall voltage when we put cells in parallel? Nothing. Having 6 of these in parallel is still 1.5 volts. So we didn't change the voltage, we didn't change the bulb resistance, so we're not changing the current. So neither the voltage nor the current is changing. Our bulb stays the same. So why would we do this? Well, theoretically, powering this bulb with the 6 cells in parallel ought to make it last 6 times as long. But it doesn't get any brighter. Now we're going to see what happens to the brightness of bulbs if we connect more than one bulb together. We're going to connect them in series and we're going to connect them in parallel. So I'm going to start out with my bulb connected to all 6 cells. I'm going to use a switch this time, and we're going to have a single bulb connected to the switch, connected to our 6 dry cells, which gives us about 9 volts. 6 times 1.5. I close the switch, and you can see how bright the bulb is. So, as more and more bulbs are added in series, I'm going to take a second bulb that's identical to this one, and I'm going to add it in. Now, another good thing about using the Christmas tree bulbs is you can twist them together. You don't have to have another alligator clip wire. So, here, remember, was the 1 bulb. Now we go with 2. What happened to the brightness? We can add in a 3rd bulb. So I'll go down the road. Here's 1 bulb, 2 bulbs, 3 bulbs. And we'll add in 1 more. I'll add in a 4th bulb. These bulbs are in series. The same current goes through each bulb when they're in series. Remember, current stays the same in series. So there are 4 bulbs in series versus 3, 2, and 1. So obviously, as more and more bulbs are added in series, the bulbs become dimmer. So why do the bulbs get dimmer? Well, again, there's 2 ways to look at this. We've got 9 volts here. Voltage adds in series. So this bulb plus that bulb plus that bulb plus that bulb's voltage, V1 plus V2 plus V3 plus V4 equals 9. And since all these bulbs are identical, the voltage divides evenly. So 9/4, which would be 2.25, each bulb only gets 2.25 volts. If there's 3 bulbs, each bulb gets 9 volts divided by 3 volts apiece. If there's 2 bulbs, they each get 4.5 volts. 1 bulb, it gets all 9. So one way to explain why they get dimmer is that the voltage divides among more bulbs. Each bulb gets less voltage. Another way to look at it is these are resistors. As you put more and more resistors in series, your total resistance goes up. When total resistance goes up, total current goes down. So putting more bulbs in series makes our current go down. So each bulb gets less current as you add more and more in. So less current makes them dimmer, less voltage makes them dimmer. Remember, power is volts times current. And when we put them in series, both voltage and current are going down. Now, how does the brightness of each bulb compare to each other? Well, they're all equally bright. Why are they all equally bright? Well, when they're in series, they all get the same current. They all get the same current. And because they're all in series and the voltage is divided among each one, they all have the same voltage. So they're all the same brightness because they all have the same voltage, they all have the same current. What happens if one bulb goes out? Now, when a bulb goes out, the filament in it is actually melting in two. And so instead of cutting the filament, I'm just going to disconnect the circuit. And you think, well, what if I disconnect the circuit right here? Well, they'll all go out. But what if I disconnect right here? Would this one still burn and only those three go out? Or would it be these three stay on and that one go out? Or what if I disconnected it right here? Would two of them stay on and the other two go out? Well, let's see. I'm going to disconnect it right here. Oh, they all went out. Not just one. What if I disconnect it in the... I already disconnected it there. I didn't want to do that again. What if I disconnect it between here? Oh, they all go out. When one bulb goes out, they all go out. Why is that? Why don't some of them stay on? Well, they all go out because current stops flowing. If I open the switch, we have no complete circuit. Our circuit is open. You have to have a complete circuit for current to flow. So if a bulb goes out, current stops flowing. When the switch is closed, do all the bulbs come on at the same time, or do they come on in order? I close the switch. Do they come on this one, then this one, then this one, then this one? Some people would say this one comes on first, that, in order. Some people say no, it would go the other way. This one would be first, second, third, and fourth. Some people say, oh, when you close the switch, the current goes both directions, and the two on the outside light up first, and the two on the inside light up afterward. So when I close the switch, it looks like they're all coming on at the same time, but are they all coming on at the same time, or is it in order, but it happens so fast we can't tell? Well, they actually all come on at the same time. When the switch is closed, electrons that are already in each bulb all start moving at the same time. The electrons aren't standing here at the switch ready for the switch to be closed, and then they run through the wire and then get to this bulb first, then that bulb, then that bulb. Electrons fill the wire, fill the bulbs. As soon as the switch is closed, all of the electrons that are already in the bulbs all start moving at the same time. There is no time delay. This would be like if your car is the 7th car back at the red light and the light turned green. What if everybody stepped on the gas at the same time? There wouldn't be any delay. So electrons are better drivers than people. As soon as you say go, they all start moving at the same time. So that's bulbs connected in series. Well, what if we connect bulbs in parallel? So we'll look at the same thing, but bulbs in parallel. So here's our single bulb. Hopefully it won't burn out. With 9 volts on it, it comes close. Something that students really always love to do is give me some more dry cells and let's see how much it takes to burn it out. And at a penny or two a bulb, it's okay to burn them out. But I'm going to put another bulb in parallel. So they're going to be connected not in a row, but together. So I'm going to connect end to end and end to end. This is a parallel connection. And then I'm going to put my alligator clip wire on each one. Now these are parallel. If I want to put another bulb in parallel with them, I go from there to here. Now notice, as I put another bulb in parallel, what happens to the brightness of the other two? They don't change. What if I put a fourth one in parallel? fourth one, would they still all be the same brightness? Certainly looks like it. I can keep them all together. So 4 bulbs in parallel. The one bulb by itself didn't change its brightness when we added a second. Those 2 didn't change when we added a third. They didn't change when we added a fourth. So as more bulbs are connected in parallel, the brightness doesn't change. Well, why not? Well, when you put them in parallel, the current has 4 different paths it could take. So each bulb gets the full 9 volts. They also all get the same current. Now when you put 4 bulbs in parallel, you have 1/4 as much resistance. If you have 1/4 as much resistance, you get 4 times as much current. Well, that 4 times as much current splits 4 ways. It's just like saying I've got $100 for one person, or $200 for 2 people, or $400 for 4 people. You keep the same amount of money regardless. Here we have 4 times as much current, but it splits 4 ways. With 3 bulbs, we get 1/3 the resistance, which gives us 3 times as much current, but it splits 3 ways. With 2 bulbs, we get twice as much current, but it splits 2 ways. So they keep the same current no matter what. So theoretically, we could just keep adding more and more bulbs, and we could power this whole building with bulbs in parallel. So why don't we do that? Well, if we're producing 4 times as much current, then the batteries will only last 1/4 as long. So the more current these batteries have to deliver, the sooner they go dead. There's also a limit. If we got up to 12, 13 bulbs, they would stop staying the same brightness because their resistance would get so low that the battery's own internal resistance would limit how much current it could deliver, and they wouldn't keep staying the same brightness. But for a minimal number of bulbs, more and more keep the same brightness. Why are they all equally bright? Well, again, they all have the same current, they all have the same voltage, which means they all have the same power. Power is V times I. What if one bulb goes out? What happens to the other? Well, if I disconnect one bulb, the others stay on and they don't change their brightness. I disconnect another, the others still stay on and don't change their brightness. Why do they all stay on? Because if you disconnect one bulb, you still have a complete circuit through the other bulbs. So you still have a complete circuit. What about closing the switch? Do the bulbs come on in order or at the same time? And it certainly looks like they come on at the same time. So why do they come on at the same time? Because as soon as the circuit is closed, current starts flowing in all parts of the circuit at the same time. The electrons that are already inside the bulb start moving. So, to summarize, the brightness of a bulb depends on how much electrical energy is converted into light energy each second. If the bulbs are otherwise identical to each other, which means they have the same resistance, the bulbs that get the most energy each second will be the bulbs that have the most current flowing through them or have the most potential difference, voltage, across them. In most cases, it's easiest to determine the brightness order by considering the amount of current flowing through the bulb rather than the drop in electric potential difference across them. So one thing you have to remember is that current follows the path of least resistance. When we have a combination circuit, the paths through the circuit that have the greatest total resistance will have the least current flowing through them, or paths that have the least total resistance will have the most current flowing through them. So we can build combination circuits. In fact, the first one that you will build on your computer simulation, I will build here live. So I've got a parallel circuit with two bulbs in series in one branch and one bulb by itself. So when current flows through this circuit, when it gets right here, it splits. It has the option of going through this bottom part that has two bulbs or the top part that has one. So the current splits, has two different paths it can follow. Which path has the most resistance? Say, well, the path up here that has two bulbs in it. Two bulbs in series are twice as much resistance as the one bulb by itself. So when the current gets to this spot, it's not going to split evenly. More current is going to go through the path that has the least resistance. That's the bottom half. So we expect the bottom bulb right here to be brighter than these other two. So when I close the switch, that's exactly what you see. The single bulb by itself is brighter than the other two. The current did not split evenly. More current went through the bottom part, which made this bulb brighter. Less current went through the top part, which made these two bulbs dimmer. So with multiple bulbs and our wires, we can twist them together in all types of combination arrangements, and we can compare brightnesses of bulbs. But remember, bulbs that have the most current going through them will be brighter than bulbs that have less current going through them.